Hello there. I hope you're doing well today. Now, there's a video that I made which you can able to find its link up here about the introduction to momentum, where we discussed about definition of momentum, how momentum is related to the resultant force, that is F is equal to change in momentum over time t, and how impulse is also related to momentum. I would advise that you kindly have a look at that video before we continue with today's video. Now today I want us to talk about conservation of momentum. Now you realize that we have the laws of conservation in physics, the conservation of energy, conservation of mass. Of course, mass and energy are related. And then we also have conservation of angular momentum. Today I want us to focus only on conservation of linear momentum. But you realize that as we're talking about the conservation of linear momentum, we cannot refuse to talk about the conservation of energy, that energy can be transferred from one point to another due to the work done, which is actually due to force. Now, how do we state the law of conservation of energy? So we are saying that when two or more objects act on each other, their total momentum remains constant provided there is no external forces that are acting on the object. In a simple term, what you're saying is that when you work out the momentum of two objects before they collide, you write somewhere, and you find their momentum after they have collided, then the momentum before collision should be equal to momentum after collision. Now, if you look at this simple demonstration here, where two marbles are pushed on either side so that they collide at a given point. So if we can able to work out the momentum of each marble and then add them before they collide, and then we compare with momentum after they have collided, then we expect the momentum is supposed to be conserved. Now, suppose one marble is stationary and we make one to move. What will happen? You can able to see clearly that this marble hits the stationary marble and it remains stationary. But then the other one, the marble 2, moves. So what is happening here? So there's some transfer of energy and there's also conservation of momentum. The marbles are having the same mass. So if marble 1 hits marble 2, that energy is transferred to marble 2, as you can able to see. Now, if we have, let's say, 3 marbles at the center, as you can able to see, then we make one marble, we push one marble to collide with the 3 marbles. What do you observe? What do you expect? You can pause the video. What do you expect? Now you can see that one marble displaces only one marble from the group of 3. That seems to be weird, eh? It's an odd experience. Now, so let's look at if there are 2 marbles. So we have 3 marbles at the center, but then want us now to have 2 marbles coming in contact with the 3, and then let's see, will it displace all the marbles? Will it displace one marble, or will it displace 2 marbles? And the question is why? Now, so if we push it, you can able to see, oh, just the way we didn't even expect. So 2 marbles only displaces the 2 marbles. Our question is why? What's going on? Even if we make one marble to move at a higher speed, why is that it only displaces only one marble? Why not all? This explains that energy in this kind of system, both energy and momentum, are supposed to be conserved. They're supposed to remain the same. So if energy, if you look at when we push a marble, we are giving it kinetic energy. That kinetic energy is transferred to the system which is enough to push only one marble. Now, if we were to concentrate only on energy, then we expected that the whole of the marbles, all the marbles are supposed to move. Maybe with less speed, but they're supposed to move. That tells us that apart from the energy that's supposed to be conserved, then it means there is something else that is conserved, and that is momentum. That is why one marble only displaces one marble, because both the law of conservation of energy and the law of conservation of momentum, linear momentum, they are supposed to be respected in such kind of a system. The kind of collision we have demonstrated here, this is called elastic collision. Elastic collision is where both kinetic energy and momentum are conserved. After the collision, the bodies move with different velocities. One body can remain stationary and the other one continues to move. Or both of them can move in opposite direction, or both of them can move in one direction. That is elastic collision. In elastic collision, which we haven't demonstrated, this is where bodies collide and stick together after collision. So after collision, those bodies move as one body, so we can able to find their common velocity. Imagine a tractor colliding with a car. So they collide, if they're at high speed, they collide such that the tractor with the car moves together as one body. Now, momentum is also conserved in explosions. Before the explosion, the momentum is zero. After the explosion, the bodies move in different directions, such that the resultant momentum after explosion remain zero. Now, let's look at a few questions that involve the knowledge that we just learned. Now, there are some simple questions here. I want us to do two, then we can able to look at a few questions also from the past papers. Now, question number one, a track of mass. So we have a track of mass 0.5 kilogram moving at 1.2 meters per second. It collides and remains attached to another initially stationary track of mass 1.5 kilogram. Calculate the common velocity of the tracks after they have collided. Now, we calculate track 1. Now, track 1 has a mass, let's say M1. So track 1, M1 is 0.5 kilogram, and its initial velocity, which you can call U1, is 1.2 meters per second. Now track 2 initially, of course, track 2 has a mass of 1.5 kilogram, and its initial velocity, it is stationary. That means the initial velocity is 0 meters per second. Now from here, we know from our previous video, which you can able to find here, momentum is given by mass times velocity. So from here, the momentum of track 1 is given by 0.5 kilogram times 1.2 meters per second. This gives us 0.6 kilogram meters per second. Now, momentum of track 2 is given by 1.5 kilogram times 0 meters per second. This gives us 0 kilogram meters per second. Now, before the tracks collide, so before collision, the total momentum of the system is 0.6 kilogram meters per second plus 0 kilogram meters per second, which gives us 0.6 kilogram meters per second. So this is the total momentum of the system before they collide. Now there's something here that I want to mention. When we say that total momentum of the system remain the same, we don't mean the individual objects, the individual bodies which are moving. Remember, for our case, the marbles, before they collide and after they have collided, you can able to see there's a change in speed. So momentum for each marble, momentum for each body in a collision can change. When we say that total momentum of a system is constant, we mean when we consider all of them together, but not just a single object. Now, after collision, so after the collision, remember, momentum before collision is equal to momentum after collision. So after collision, the total momentum is 0.6, which will be equal to total mass times the common velocity. Why are we talking about total mass? These tracks, we have been told that they are going to stick together after collision. That means they're going to behave like one body. So we just add their masses. When bodies stick together, they are having the same velocity, because they are now together. They are now like this together, so moving as one body. So 0.6 is equal to 0.5 plus 1.5 times v. So 0.6 is equal to 2v, and therefore v is 0.6 divided by 2, 0.6 divided by 2, which gives us 0.3 meters per second. 0.3 meters per second. So those bodies, after collision, they will move at a common velocity of 0.3. A car of mass 1000 kg moving at 20 meters per second makes a head-on collision with a lorry of mass 2000 kg moving at 16 meters per second. Calculate their common velocity after the collision if they remain attached to each other. Now, so we have the car. So momentum of the car, remember momentum, once again, momentum is given by mass times velocity. So momentum of the car is going to be equal to its mass, which is 1000 kg, times velocity, which is 20 meters per second, and this gives us 20,000 kilogram meters per second. Now it is colliding head-on with a lorry. It is colliding head-on with a lorry. Now for this case, as you can able to see, I have taken the velocity of the car to be positive. The mass of the lorry is 2000, so that is 2000 kilogram times its speed, which is 16 meters per second. But because we have taken the direction of the car to be positive, that means the direction of the lorry, we take it as the negative. You can also try calculating by taking this to be negative and taking this to be positive, and then we see if we can make the same conclusion. Now this will give us negative 32,000 kilogram meters per second. Remember, when I write this, meters per second is the same as like this. It's the same thing. So meters per second, but we don't need to mix. So just use meters per second like that. Per second. Now, so the total momentum before collision is going to be 20,000 plus negative 32,000, which you get negative 12,000 kilogram meters per second. Kilogram meters per second. So momentum before collision should be equal to momentum after collision. So after collision, the momentum should also be minus 12,000 kilogram meters per second. Now these bodies are going to remain attached to each other. So that means they are going to have a common velocity. So their masses is just going to be, we are going to add the mass of the car and the lorry, because it's like they are going to be attached to each other. The collision was too high. So we add the masses, 1,000 plus 2,000, because the bodies are going to behave like one body. So that is 3,000 kilogram times the common velocity v. So this is a kilogram. So if you divide both sides by v by 3,000, so v is equal to minus 12,000 kilogram meters per second divided by 3,000 kilogram. And of course you can see clearly, kilogram cancel kilogram, 0, 0, 0, 0, 0, 0. So the answer here is negative 4 meters per second. Now the question is, what is now the significance of this negative? Pause the video. What is the significance of the negative? Now the negative shows that these bodies, if this was the lorry, let's say this direction, this is the lorry, and this is the car, we took the direction of the car to be positive, we took the direction of the lorry to be negative. So because the common velocity is negative 4 meters per second, so it therefore means that after these bodies collide, then they are going to move in the direction of the initial direction of the lorry. That is what the negative represents. Now let's look at a past paper question. I got this question from one of the Cambridge past papers. Now let's look at it. IGCSE. Yeah. Now the figure shows two cars, A and B, before they collide. So we have a stationary car, car B, and we have another car, that is car A, which is moving at 18 meters per second. Now car B of mass 1,200 kilogram is stationary. Car A of mass 2,000 is traveling towards car B at 18 meters per second. Part A, calculate the momentum of car A. Part A, calculate the momentum of car A. Now, momentum is given by mass times velocity. So therefore, momentum of car A, I'll write PA, momentum of car A is given by, that is the mass of car A is 2,000. So 2,000 kilogram times its velocity, which is 18 meters per second. So this gives us 36,000 kilogram meters per second. That is 2 free marks. Those are free marks. Now, part B, Roman 1. The cars collides and car B experience an impulse. Car A continues to move in the same direction with a momentum of 21,000 kilogram meters per second. Calculate the momentum of car B immediately after the collision. Now, this part of this question is testing the law of conservation of momentum. That momentum before a collision should be equal to momentum after collision for a given system. Now, after collision, momentum of car B. So this is part B, Roman 1. So after collision, momentum of car B is now 21,000 kilogram meters per second. That is momentum, momentum of car A. This is momentum of car A. So momentum of car A is 21,000 kilogram meters per second. Remember, B was stationary. So that means if we're supposed to look at momentum before collision, that of A is 36,000. Momentum of B is 0. It is stationary. That means the total momentum before collision is still 36,000. But after they have collided, momentum of A has changed from 36 to 21. So now, momentum of B, calculate the momentum of B. So momentum of B will be 36,000, which is the total momentum, minus the momentum of car A, which is 21,000, and this gives us 15,000 kilogram meters per second. Now remember, initially, because the car B was stationary, so its initial momentum was 0. So initial momentum of car B was 0 kilogram meters per second. But now after collision, momentum is now 15,000 kilogram meters per second. So 15,000 minus 0 gives us 15,000 kilogram meters per second. And that is the change in momentum for car B. Roman 2, determine the average impulse experienced by car B during the collision. This is something that we did in our previous video, which you can always go back and check. Now, we said that impulse is defined as the product of force and time. But from the question, you can be able to see we don't even have time, we don't even have force of impact. Can just confirm, yeah, we don't have force and time. That means we use the other formula. So we know that impulse is also given by what? Change in momentum. So for this case, the change in momentum for car B is already here, which is 15,000 kilograms. So 15,000 kilogram meters per second, or we can just use Newton second as the unit of impulse. Should you have a problem with the unit, kindly revisit or kindly check the other video about that. So Roman 3, the cars are in contact for 0.2. So the time here, we are now given time here, 0.20 seconds. Calculate the average resultant force experienced by car B during the collision. So from this formula here, impulse is 15,000, which is equal to force F times time, which is 0.2. So therefore F is equal to 15,000 divided by 0.2. And this should be equal, is it 75,000? Let's just confirm. Divided by 0.2, and that is 75,000 newtons. 75,000 newtons as the average force experienced by the object. Questions. Now, part C of the question. A modern car is designed so that during a collision, the front section of the car is crushed and the time of contact increases. Explain the benefit of increasing the time of contact for the people in the car. Now, if you can remember, F is given by change in momentum over time t. For the same change in momentum, the force of impact is inversely proportional to the time t. Increasing this time t decreases the impact of force. So what is the benefit? The benefit is that the passengers are not injured, or they are less injured. So they are less injured, or there is no injuries at all. Why? Because when time is increased, then the resultant impulsive force decreases. And that is enough. If you want more questions, If there's something here that you have done, you don't get it, kindly comment below or reach us via this number that you can able to see on the screen.